Let's calculate the dot product of two vectors if those two vectors are given in component notation. So let's assume I have two vectors A and B. A can be decomposed as usual as AX and AY, AX being along the X direction and AY being along the Y direction. Similarly, I would like to add this vector to, I would like to take the dot product of this vector with another vector B, such that B has been decomposed with two vectors Bx and By, with Bx along the X direction and By along the Y direction. In order to dot those two vectors, I'm going to use the exact same rule as the rule we used to use when we would multiply the sum of two scalars, and we would be using the distributivity rule. It will work the exact same way. So A will be replaced by AX plus AY dot B will be replaced by BX plus BY. And what I will do is I will actually use the general form AXI IJ AYJ with BXI and BYJ, and you can do the exact same process in 3 dimensions. I will only do the 2 dimensions because it's less work. But please practice in 3D exactly the same technique, except a little bit more terms going around. So this will be AXI plus AYJ dot BXI plus BYJ. So again, I'm going to take the first term, dot it with this first term, then go back to this first term, dot it with this second term, etc, etc. So this dot this plus this dot this plus this dot this plus this dot this, the standard distributivity rule. I will end up with AX times BX I dot I. When you multiply a vector by a scalar, those two commute. So if you have a scalar times a vector dot another scalar and another vector, you can gather around all the scalars together, and you can even commute the two vectors as you take their dot product, because the dot product is following the commutativity rule. That is, I dot j is the same as j dot I. So first term will give me AX BX times I dot I. The second term will give me AX BY I dot j. The third term will give me AY BX j dot I, and the last term will be AY BY j dot j. So now I have a bunch of terms here. Let's figure out what to do with them. Let's start with this one. I is in this direction, and I know that its length is equal to 1. J is in the j direction, the y direction, so perpendicular to I, and I know that it has the length of 1. And I know from the property of the dot product that if two vectors are perpendicular, the angle between the two is 90 degrees, therefore the cosine is 0, therefore I dot j will give me 0. Since the dot product commute, j dot I will also give me 0, which means that this term and this term are just 0. Similarly, I will need to calculate I dot I and j dot j, which will be the case where I and I, or j dot j, are two vectors parallel to each other and in the same direction. Therefore, the dot product will take its maximum value. The angle between the two vectors is 0, the cosine is 1, therefore I dot I is magnitude of I, which is 1, times magnitude of I, which is 1, times the cosine of 0, which is 1. Therefore, I dot I is equal to 1, and similarly, j dot j is equal to 1. Again, if you do it in 3D, you will have more terms such that I dot k, k dot j, k dot I, all those guys will be equal to 0. And similarly, you will end up with k dot k in 3D, which also will be equal to 1. Therefore, the two other terms can be reduced by just the sum of the product ax bx and ay by. So a dot b is equal to ax times bx plus ay times by. So all you have to do to take the dot product of two vectors is to multiply all their x component together, multiply all their y component together, and add them up. And sure enough, you have to end up with a scalar.